Welcome everyone to this session on mechanical integrity. Today, we're going to explore a vital perspective. When does maintenance stop being just a routine task and start becoming the foundation of process safety? In our industry, containment isn't just a goal, it's the product. Our primary job is to ensure that what's inside the pipes and vessels stays there, and maintenance is the frontline protector of that boundary. Over the next hour, we'll look at how we move from simply doing work to providing technical assurance. Let's start with a shift in mindset, the process safety promise. An inspection date in your CMS isn't just a calendar entry. It's a promise to every person standing near that plant that the equipment is safe to operate. A vessel or pipe doesn't magically become safe because a work order exists. Safety is only achieved when we know the actual condition, compare it against a valid limit, and act on it before that limit is breached. This brings us to our central argument. Mechanical integrity is essentially a closed-loop control system for process safety. Activity alone is not assurance. To close this loop, we must start with a solid design basis, choose the right inspection methods, make a clear engineering decision on the results, correct any deficiencies, and verify the repair. Only by learning from these findings and updating our intervals can we truly say the primary containment is within safe limits. To guide our discussion today, I've mapped out 7 key controls that transform maintenance into process safety. We will follow the life cycle of an integrity decision, from understanding our purpose and technical basis to collecting evidence, making decisions, ensuring competence, and finally, governing the process and correcting issues. Every single one of these controls must help us answer one fundamental question. What evidence allows this equipment to remain in hazardous service? In this first section, we'll define the boundary. Maintenance officially becomes process safety the moment a failure could release hazardous energy, defeat a safeguard, or prevent a safe shutdown. It's no longer just about uptime. It's about preventing catastrophe. To be clear, mechanical integrity is not just a stack of NDT reports or a high compliance percentage on a dashboard. It is the known condition of equipment compared against a valid technical basis. It's not just completing a work order. It's making a documented decision against explicit criteria and ensuring that every repair is verified before the equipment returns to service. We often talk about reliability and process safety in the same breath, but their lenses are different. While reliability focuses on function, output, and economic optimization, the process safety lens is focused on containment and protecting people. When we defer a safety inspection, we aren't just making a production trade-off. We are making an explicit risk decision that requires new safeguards. From a regulatory standpoint, OSHA and EPA provide clear frameworks for what equipment falls under this umbrella. It covers everything from pressure vessels and piping to relief systems and emergency shutdowns. Even the quality assurance of new installations and the suitability of spare parts are critical components of the mechanical integrity scope. Mechanical integrity is a life cycle assurance system, not just an inspection department. It begins at the drafting table when we specify materials and codes, continues through fabrication and installation, and stays active throughout operation until the asset is safely retired. If we ignore any of these stages, the loop is broken. It's important to remember that a major incident starts long before the leak occurs. The pathway to failure usually involves a chain of defeated assumptions. A damage mechanism is missed, a blind spot, an inspection coverage exists, or a weak decision is made during an engineering review. By the time the boundary fails, the system has already let us down multiple times. We must also apply barrier thinking. Mechanical integrity protects the primary containment, like pipes and vessels, but it also ensures our control systems, isolation valves, and human procedures are ready to act. A safeguard might be physically there, but if it hasn't been tested, it is functionally unavailable. Let's look at a real-world example. The 2010 Tesoro Anacortes tragedy. 7 people lost their lives when a heat exchanger ruptured due to high-temperature hydrogen attack. The failure wasn't due to a lack of effort, but because of an assumed safe operating region and the use of inspection methods that simply couldn't detect the specific damage mechanism occurring. The lessons from Tesoro are vital. First, never treat industry models as immunity. always challenge the operating envelope. Second, your inspection method must match the damage morphology. If you have high consequence equipment with uncertain damage, you must lean toward conservative engineering or, better yet, inherent safety through material upgrades. Another case is the 2012 Chevron Richmond fire. Here, a pipe ruptured because of sulfidation corrosion. The control failure was simple but devastating. The measurement locations didn't represent the actual vulnerable component. Taking good readings at the wrong spot creates a dangerous, false sense of confidence. Chevron taught us that data must be representative. We need to understand material variability even in similar pipes and place measurements at the most susceptible points, not just the easiest ones to reach. Furthermore, repeated recommendations that are ignored are essentially risk decisions that have been made by default. Comparing these two cases shows that while the mechanisms were different, the broken control loops were the same. Both involved underestimated risks, weak inspection placement, and failure to act on known uncertainties. The question for your program is, who owns the uncertainty in your data? Now that we understand the stakes, let's talk about building the technical basis. A program is only as good as its foundation. A complete equipment register, a clear design basis, and a deep understanding of how things fail. Everything starts with the equipment register. If an asset isn't on your map, it isn't being inspected. We need to reconcile P&IDs and field walkdowns to ensure every circuit, valve, and relief device is accounted for, along with its design limits and credible damage mechanisms. Your acceptance decisions are only as strong as your design basis. Common gaps include treating nameplate data as a complete record or failing to update drawings after modification. Without knowing the original design code and intended service, you cannot accurately determine if a piece of equipment is still fit for purpose. A damage mechanism review is the process of turning process conditions into testable hypotheses. By looking at service fluid, temperature, and materials, we determine where, how fast, and in what shape degradation will occur. This review should directly dictate what, where, and how often you inspect. We also have to consider operating limits. Process excursions aren't just operations data, they're integrity consumption. If you operate in an alert or action window, the damage rate may accelerate, and your inspection program must react to that specific exposure immediately. Risk is a product of consequence and likelihood. While evidence is required for all equipment, the rigor of that evidence changes based on criticality. For high consequence assets, we need higher engineering authority, more redundant coverage, and tighter intervals for deferral approvals. There are two main strategies: fixed interval and risk-based inspection, RBI. While RBI allows us to focus resources where risk is highest, it is heavily dependent on data quality. It is never an excuse to ignore statutory maximums or operate with unknown conditions. Strategy must be driven by failure morphology. If you're looking for pitting, a sparse spot reading with UT is useless. You need a dense scan. If you're worried about CUI, screening is just the start. You eventually have to pull the insulation. Choose the tool based on the threat, not what's easiest to carry. Finally, an inspection plan should be an engineering instruction, not just a due date. It needs to define the exact component, the calibration requirements, specific locations to scan, and the clear acceptance limits. This removes ambiguity for the person in the field. Moving on to Section 3, Inspection and Testing. This is where we validate the evidence. We must select the right technology for the specific damage mechanism and ensure our data is high quality enough to support a defensible decision. Visual examination is the most common tool. It's great for detecting leaks, distortion, and vibration, but it's limited to surface evidence. A good visual report isn't just visual okay. It's a detailed record of defined anomalies with scale and location. UT thickness measurement is excellent for general wall loss, but it has blind spots. Spot readings can easily miss localized corrosion. To make this actionable, we must record raw readings and exact coordinates to ensure we can trend findings over time. 4-welds, PUT, and TOFD offer sophisticated detection of internal flaws. However, these techniques aren't magic. They require qualified procedures and expert interpretation. For critical calls, independent review of the encoded data is a must. We often use a combination of surface and radiographic methods to reduce blind spots. Whether it's RT for volume, MT for surface cracks, or PMI for material identity, each has a strength and a specific limit. Never rely on just one method if the damage mechanism is complex. Corrosion under insulation, CUI, requires a special approach. We screen broadly using risk profiles and guided waves, but the final decision requires opening the insulation at target areas like supports and low points. Remember, the restored insulation system is itself a critical control. Pressure and functional tests are only valid if we define the objective beforehand. What failure mode are we challenging? We must ensure the test boundary is complete and that all temporary blinds or jumpers are removed after the test to restore the normal safe configuration. Relief devices are safety functions, not maintenance commodities. The bench test result is only part of the story. The inlet and outlet piping and the installed orientation matter just as much. Any as-found failure should be treated as a process safety signal, not just a repair task. Rotating equipment, like process pumps, acts as both a containment boundary and a shutdown dependency. We must monitor not just the seals and casings, but also the vibration, temperature, and protective trips that prevent a catastrophic mechanical failure. When testing controls and interlocks, we must test the entire path, not just the device. This means applying a known input to the sensor, verifying the logic, and confirming the final valve or motor actually actuates. A partial test provides a false sense of security. Finally, we evaluate inspection effectiveness across 6 dimensions. Did we have the right capability and coverage? Were the personnel skilled and the surface conditions suitable? If any of these are weak, the resulting evidence shouldn't be trusted for high-risk decisions. In Section 4, we discuss how measurements become safety decisions. A number on a page is meaningless until it's compared against a traceable limit and reviewed by a competent authority. We follow an acceptance hierarchy. It starts with law and regulation, moves through jurisdiction and design codes, and includes site standards and manufacturer limits. The final word is often an engineering disposition, like a fitness for service calculation or a re-rate. Every inspection result should land in one of 3 clear states: accept, monitor, or deficient. Avoid vague terms like satisfactory for now. If it's deficient, it must be removed, restricted, or corrected. If it's in monitoring, you must name the decision owner and define a clear trigger for action. Thickness decisions require more than just a trend line. We must calculate the corrosion rate and indicative remaining life based on a validated required thickness. Remember that measurement error and localized loss consume your safety margin. Fitness for service, FFS, assessments such as API 579 allow us to analyze complex damage. As the damage becomes more complex, we move from simple screening to advanced analysis. However, advanced math never compensates for poor data or an unknown damage mechanism. We must distinguish between temporary and permanent repairs. A temporary repair needs a defined life and a visible status, so it doesn't become part of the invisible plant fabric. A permanent repair must restore the original design basis and include a verified return to service. An engineering disposition has only 5 defensible destinations: repair, replace, re-rate, monitor, or retire. Importantly, choosing to continue as is a technical decision that requires a safe basis. It is not simply the absence of decision. Section 5 focuses on the who and the how: procedures, qualifications, and quality assurance. Integrity work must be executed by competent people using controlled methods. A good procedure controls technical variables. It should specify the exact equipment, prerequisites like lighting and surface cleanliness, and clear sequences for the scan plan. If the procedure is too complex for the task risk, it won't be followed. If it's too simple, the results won't be repeatable. Procedure control is a loop. It must be authored by a technical owner, validated for the specific application, and approved by an authorized reviewer. Most importantly, the field crew must have the correct revision at the point of work and a way to provide feedback for improvement. Certification is not the same as competence. While ASNE levels 1, 2, and 3 define general roles, we must verify that the individual has the specific application experience and vision required for the job at hand. Application competence is what ultimately decides quality. A repair package is more than a welding task. It's an engineering design that qualifies the materials, the welder, the execution steps like preheat, and the final NDE. The package isn't closed until the as-built record and return to service approval are complete. Many plants outsource execution, but you cannot outsource accountability. As the owner-user, you must define the scope and deliverables, approve the procedures, and authorize the final disposition. The contractor provides the evidence, but you own the risk. Material quality assurance is critical because the wrong alloy can look perfect until it fails in service. We must verify materials at receipt and installation, especially in high-consequence service where a mix-up could lead to rapid corrosion or brittle fracture. Finally, no modification is complete until the integrity program is updated. During the management of change, MOC, and pre-startup safety review, PSSR, we must ensure that drawings, equipment registers, and inspection tasks are all adjusted to reflect the new reality. In Section 6, we tackle documentation and overdue work. Records are the evidence chain that justifies continued service. Overdue work isn't just a schedule delay, it's a risk decision. OSHA requires specific core data in every record: date, person, ID, description, and results. However, a strong program goes further, capturing the instrument settings, exact coordinates, and the raw evidence like images or scans to ensure the decision can be reconstructed years later. We must maintain an unbroken evidence chain. Raw data leads to a result, which leads to a disposition, which leads to work. If these steps are stored in separate, disconnected systems, the engineering logic is lost. We need a single equipment ID to connect everything from design to history. Let's be blunt. An overdue inspection is an extension of risk. The due date is the end of an approved knowledge interval. If you pass that date without a decision, you are operating on evidence that your own program has judged to be insufficient. We need a deferral gate. If work won't be done by the due date, we must either demonstrate a safe basis for a controlled extension with new safeguards and a firm expiry, or we must reduce exposure and shut down. We must never normalize the practice of ignoring due dates. Interim safeguards are used to buy time, not to erase a deficiency. This might mean lowering pressure, increasing the frequency of leak rounds, or restricting occupancy in the area. These measures must be visible to management and sustainable by operations. To measure integrity performance, look at a portfolio of indicators. Don't just look at percent on time. Look at effective coverage, the age of open deficiencies, and the quality of the data. High rates of as-found failures in relief valves or repeat damage in the same location are red flags. Our final section, Section 7, covers correcting deficiencies and proving safe return. A finding is only closed when we've proven the safety function has been restored. When a condition is outside the acceptable limit, we face a decision tree. If safe operation cannot be assured right now, we must remove the exposure. If we can operate safely for a short time, we apply interim safeguard while we plan the repair or replacement. The handoff from engineering to the work floor is critical. A work order that just says repair leak is not enough. Engineering must provide the exact boundary, materials, and NDE requirements, while maintenance delivers the sequence plan and qualified personnel. Quality assurance must be built into the job, not inspected in at the end. This means witnessing hold points, controlling fit-up and cleanliness, and documenting as-built conditions at each step. Quality control is a sequence of releases, not a final signature. Before an asset returns to service, we must answer 5 questions. Is the technical design met? Did the test pass? Are the blinds and safeguards restored? Do operations understand the limits? And finally, has the authorized authority signed off? We must also close the learning loop. Every finding should be compared against what we predicted. If a pipe corroded faster than expected, we need to know why and update our plans, intervals, and procedures accordingly. A repair without a program update invites the same surprise to happen again. Roles and cadence matter. Everyone from operations to leadership has a part to play. We need to make these accountabilities clear. Who reports excursions, who plans the exams, and who governs the risk of overdue work before an anomaly arrives. If you're looking to improve your program, here is a 90-day roadmap. Spend the first month seeing your exposure, the second month repairing your controls and deferral gates, and the third month proving the loop by completing high-risk exams and publishing what you've learned. As seasoned practitioners, we see common failures, measuring activity instead of effectiveness, or letting RBI be used as a data-free extension tool. The correction is always to return to technical rigor, audit the method capability, control the limits, and require a safe basis for every extension. This reference architecture provides a map of the standards we've discussed today, from OSHA's PSM requirements to API inspection codes and ASME repair standards. These are the tools you use to build a defensible program. For further learning, I highly recommend the CSB animations on Tesoro and Chevron. They are excellent for facilitated sessions. Pause the video at each decision point and ask your team, what evidence was missing here? As we conclude, here are 5 executive takeaways. Know your technical basis, trust evidence over activity, strictly govern your due dates, correct the underlying mechanisms of failure, and always close your work with documented proof of safety. Thank you for your time today. Remember, containment is our product, and maintenance is what protects that boundary. Name every overdue risk, decide every deficiency, and prove every repair. I'll now take any questions you may have.